Alright, thanks for watching, and today I want to define something super neat, namely the square root of a matrix. Ooh, I know, and you might be like, wow, how can you define it? Well, let's do it by analogy with real numbers. Namely, well, y is the square root of x if and only if y squared equals x, and moreover, this only works if a is positive. So a and x is greater or equal to 0. Well, the analog for matrices is the same thing, namely b is the square root of a if and only if b squared equals a and a is greater or equal to 0. But you might say, what does it mean for a matrix to be greater or equal to 0? You'll see in a second. And the cool thing is, by the way, here technically there are two values such as y squared equals x. Here there are at least n squared values where n is the size of a. So what is the analog here? Let's take this matrix A to be 5, 4, 4, 5. And what I'm going to do now, it only works for diagonalizable matrices. Maybe there's an analog for general matrices, I'm not sure. But let's take this matrix and you'll see why. Let's find all the eigenvalues and eigenvectors. So let's find lambda I minus a. Well, that's lambda minus 5, then minus 4, lambda minus 5. And this becomes lambda minus 5 squared minus 4 times minus 4, so minus 16. You set that equal to 0, and you get lambda minus 5 squared equals to 16. So lambda minus 5 is plus or minus 4. So lambda, it's either 5 minus 4, which is 1, or 5 plus 4, which is 9. And this we actually take as a definition for a matrix being greater than or equal to 0. Namely, we define a matrix to be non-negative if and only if its eigenvalues are non-negative. And this is, I did not invent this. This is actually a good definition because especially if A is symmetric, which it is here, then the eigenvalues are real, first of all. So you can really talk about this. And also the corresponding quadratic form would be positive, greater or equal to 0. So it's not too shocking. As I said, I didn't invent this. And I have done a separate video on quadratic forms if you want to check this out. Okay, that's one thing. So those are the eigenvalues. Now let's find the eigenvectors. So for lambda equals 1, we get the null space of, let's see, minus 4, minus 4, minus 4, minus 4, which is the null space of 1, 1, 0, 0. And then you can find that this is the span of 1 minus 1. Because if x plus y equals 0, then y is minus x. That's how you get this minus 1. And also, if you do lambda equals 9, then the null space of, this time 9 is so 4 minus 4, 4 minus 4. That's the null space of, so you just row reduce 1 minus 1, 0, 0. And that's the span of 1, 1. Okay, so what does that tell you? It tells you that, in fact, what we know then now is, A equals to PDP inverse equals to PDP inverse, where P is your matrix of eigenvectors, 1 minus 1, 1, 1, and D is your matrix of eigenvalues, 1, 0, 0, 9. And then 1, 1, minus 1, 1 inverse. Why is that useful? Because in several of my videos, I've shown that if A is PDP inverse, then A squared is, PDP inverse, This becomes the identity, and you get P d squared P inverse. And if you continue, you get A cubed is P d cubed P inverse. And A to the n would be P d to the n P inverse. For d to the n, because d is diagonal, this is easy to calculate. It's 1 to the n, 0, 9 to the n. And here's a nice thing. This actually also works for real numbers n. So not just integers. In particular, square root of a, which is a to the 1/2, is just p d to the 1/2 p inverse. Maybe later I'll show you why this works, but in this case, what is d to the 1/2? You just take square roots of each component. So it's 1, 1, minus 1, 1, 1, 0. So square root of 1, which is 1, 0, 0. Square root of 9, which is 3. And then 1, 1, minus 1, 1. Inverse. And then you just calculate that. So 1, 1, minus 1, 1. 1, 0, 0, 3. And there's this nice formula for the inverse of a matrix. You take the determinant. So 1 plus 1. So 2, so 1/2. You change those things, 1, 1, and you subtract. So minus 1 and 1. And you just calculate this. So 1/2, 1, 1, minus 1, 1. And then 1, 0, 0, 3. 1, 1, minus 1, 1. And you get 1/2, 1, 1, minus 1, 1. And then let's see. So probably just 1, minus 1. And then 3, 3. And you calculate that, so you get 1/2, and then I think 4, 2, 2, 42, and 4. Which becomes 1, 2, 1, 1, 2. Well, I'm claiming this is square root of a, so square root of a is 2, 1, 1, 2. Is 2, 1, 1, 2. What would that mean? It means that if you take this and you square it, so if you multiply 2, 1, 1, 2 by itself, well, let's see, we get 4, so 5, 4, 4, 5. In other words, if this is b, then b squared is this, and this gives us our original matrix A back. So indeed, it is a square root of A. And maybe as I promised, let me show you why this is true. Well, again, suppose A is P d P inverse. And square root of A is P d to the 1/2 P inverse. Then, let's take square root of A times square root of A. That's P d to the 1/2 P inverse. P d to the 1/2 P inverse. P inverse P is the identity, so we get P d to the 1/2 d to the 1/2 P inverse. But d to the 1/2 times d to the 1/2 is just d, so we get P d P inverse, and that's indeed A. So if you take the square of the square root, you indeed get your matrix A back. And the analog of positive is having all the eigenvalues positive. So, which I think it's a very nice analog of this. Alright, I hope you like this linear algebra extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.